Good morning. Today is March 14th, 2015, and today Harry Ricker is going to lead a discussion, not a presentation, on cosmology, which is a pretty broad topic, so I don't know exactly what direction he's planning to go. I'll leave that up to him. Harry, why don't you go ahead and
Let's see, Greg, I was going to make
set us on a path. Oh, Nick wants to say something?
Yes. Today, March 14th, 2015, is Einstein's 136th birthday.
There you go.
So I thought I would just say a couple of things about Einstein. He really is, I think, the ultimate dissident, because here he was in the patent office, totally out of the mainstream.
Right.
And yet he came up with some ideas that totally changed the course of history. So we're in the ironic position, sort of double-edged sword here, that every time the mainstream backs Einstein, they're backing, hey, we should listen to dissidents. On the other hand, probably the greatest consensus we have in the dissident community, Springer and Newbern aside, is that special relativity is incorrect. Mm-hmm. So we're in the ironic position as well of saying, hey, you shouldn't listen to dissidents like Einstein. So the last 110 years, I think, have been marinated in irony in that respect. The other thing I'd like to say is we can criticize special relativity, but it really wasn't Einstein's fault. He's a guy who fiddled around with ideas and presented his ideas. The problem really was that they were accepted without appropriate analysis, and I think one of the reasons why they were accepted without examination of the math and the logic is that the philosophical basis of relativity appealed to the mainstream at that time. So with that acknowledgement to Einstein, I also tried to have my Einstein hairdo today, and we'll just have Albert come up and say, on with the meeting.
Yep.
Over to you, Harry.
Okay, sounds good.
Well,
Harry,
that was very good, only I didn't hear you very well.
Yeah, I will say this, Nick, your audio, I don't know, it seems like you've had this before, kind of comes in and out, fades a little bit. It's not terrible, but it's not, it does that weird thing.
In Skype, I have no problem, but here is the one place where I come in I'll try and speak loudly if I come back.
Sounds good. Okay.
Well, I don't know what it is. I mean, I agree. Last week you weren't very loud either. So let me know if you can't hear me. Okay.
You're loud and clear. You sound great to me. So okay. Whatever that's worth, and I hope I sound okay.
Okay. In preface, I had talked to David about resuming the Saturday morning discussions, and I proposed some topics to discuss to get the ball rolling and get some interest moving forward on resuming the Saturday morning discussions. And this was one of the topics to discuss cosmology. And to a certain extent, cosmology is relativity in that it's really an application of general relativity, and it's really the only major application of general relativity. There are a few, you might argue some other ones, but as Stephen Crothers points out, there are not really many exact solutions of general relativity, and there's like the Friedmann equations, and then there's the black hole universe equation he talks about, and there are not that many exact solutions. So cosmology, although is supposed to be the science of the universe, it really kind of turns out to be mostly the science of application of general relativity to the universe. And to a certain extent, it's a lot of speculation. And I maintain it's not really science, but how can we juggle our equations of general relativity to make it look like the universe is described by our models? And I believe, and we can talk about this if you want, I believe that there's not really a whole lot of inductive science. In other words, this is what the universe looks like because we've studied it I don't think Dingle complained about this, that what he called the science of the universe and the worshiping of the universe, that science was more interested in speculation, mathematical speculation. And as time has gone on, the simple idea that we can describe the universe by these simple Friedman equations, which come out of general relativity, has really kind of become more and more difficult to sustain. And there are a lot of problems. We can talk about the problems. There's a lot of them. There's the fact the Hubble constant doesn't allow for the oldest stars are older than the universe, because the Hubble constant isn't really pinned down exactly. The Hubble constant says the universe is younger than the oldest stars. Some recent evidence, some galaxies have been found out in the young universe, the young galaxies. There are old stars in young galaxies. That's not supposed to be. So there's all these issues there. I'm going to talk a little bit about my background. When I went to college, I took a course in astronomy. I'm an electrical engineer. And the guy, professor, said to me, he told us that the universe was expanding. I thought that was a pretty incredible idea, and I didn't believe it. I still don't believe it. The other, that had a big influence on me, and I became interested in amateur astronomy. I worked at Johns Hopkins Applied Physics Laboratory for many years, and I went to a lecture by Hans Alvin. I don't know if you remember who he is, but he was famous for his matter, antimatter book, if I'm not mistaken. And he said, and you know, it's kind of different when you have somebody tell you that's really a physical person there. He said that the idea that the universe expanded from a pea was absurd. And that really kind of shocked me to hear a respected scientist say that in a scientific meeting. So that had a big influence on me. Another scientist that had a lot of influence on me was Halton Arp, which dissidents are probably more familiar with than non-dissidents. And I think we'll hear something about him. Now, we know that Alvin was a critic of Big Bang cosmology, and Halton Arp as well. Fred Hoyle invented the word Big Bang as a kind of a sarcasm, and it stuck. That's kind of amusing that something that was designed to be a criticism has become the name. And I know a number of years ago they tried to rename it unsuccessfully. So I think Fred Hoyle is another, of course, he was the inventor of the steady state cosmology. So there's a lot of scientists' names that we could talk about here. I think the main point of our discussion is going to be, what do people here think? I've sort of said a little bit about what I think. Now, here's one thing I want to talk about, which a lot of people don't deal with, and that is they don't distinguish between cosmology and cosmogony. And when I heard about cosmogony, I thought, that's interesting. And cosmogony is about how things are created. And it's the study of the creation of the world. And cosmology has sort of taken that over by trying to make general relativity, the theory of general relativity, be able to explain how the universe is created. And that leads us into this Big Bang. They don't explain what existed prior to the Big Bang. They try to explain what happened after. That leads us into the problem that they kind of can explain helium and hydrogen creation, but not anything else. So general relativity, so cosmology really is kind of limited in what it can explain as far as creation is concerned. Now, they've sort of tried to amend that theory by saying elements are created in the stars through nucleosynthesis, and then supernova blow the elements created back out into the interstellar medium, which then collapses back into form stars and planets. And so they have this cycle of creation but the observational evidence doesn't fit that very well, so that's a problem. And really what it boils down to is they can't explain all these different types of galaxies that are out there, how they are created, why they have the forms that they have. And then there's the other problem of the collapsing gas cloud hypothesis can't really explain the existence of the solar system, how the solar system formed. And I spent a lot of time studying this, and I kind of came to the conclusion, you know, you have the problem of the angular momentum. What happens to the angular momentum? There's all of these issues. You can fudge the models to make it look like that the solar system collapsed from a gas cloud, but bottom line is it's not very convincing. So there are a lot of issues that we can talk about. I'm going to turn it over to Al McDowell because he told me he has to leave at 11 o'clock. Al, do you have any comments? Would you tell us what you're thinking? Are you there? Do I have to turn him on?
I don't think so. Everybody should have the ability to turn themselves on. I see that Al is in the meeting. So, but I don't know. I guess I can try promoting him. Let's see what that does.
Well, he sent me an email saying he had to leave early, so I wanted
Al,
to.
can you acknowledge your presence in some way? We don't see you or hear you. So I'm guessing he's having technical problems, which again, we're all struggling with trying to figure out the new system. So could be something like that. What else is new? It's always a new system that everybody's trying to figure out how to use. So I don't think we're going to hear from him. He can certainly join us.
Well, I've sort of presented a very thumbnail sketch of my view.
I can give you, if you like, I'll give you some thoughts I had based on what you just said.
All right, go ahead.
Okay.
I wanted to get Al to talk because we've been having
I appreciate. Well, if you can hear me, if you're able to get your audio and visual working, I'm happy to step aside. But to fill time, at least, I'll give you my 2 cents here. I think as with so many things, there seems to be often 3 options, and I don't know, just become more aware of this recently than I had been, I guess. But there seems to be one camp, which obviously is the conventional camp, which holds to the Big Bang idea, which is a finite universe that had a beginning. And then there is another camp. I'm certain that there are quite a few here who are part of this camp who say, no, the universe is neither finite in extent, nor is it finite in terms of its age. It's always existed. So basically, variations on the theme of a steady state universe. And so then some names I can name would be Glenn Borchert, and Eric Lerner, and quite a few people that kind of fit into this category, and they make some really good arguments against the Big Bang, and they mention all the various inconsistencies. And so to the extent that they're making those arguments, I tend to agree with all those people, and I find myself agreeing with those people, although I disagree with their conclusion that therefore the universe is infinite in extent and in age. So my own personal view is that I agree with conventional thinking that the universe is finite both in extent and in terms of its age, that it did have a beginning, but I don't believe its beginning was anything like what they're claiming it was. So I don't know where that puts me, but that's my.
All right, Greg, I have a couple of comments.
I'm just simply saying that there are 2 different kinds of dissonance. There's dissonance who, so really to begin any kind of a discussion, we have to figure out which of those camps a person is in.
Well, I'm not really sure that's the issue. Here's my comment. My comment is that anything that you just talked about, science, is it subject to any kind of testability criterion?
I believe it is. In fact, it's my contention that gravity itself would not exist if we lived in an infinite universe, that the actual size of the universe is significant. And the size of the universe in relation to the size of the atom, those 2 things which are measurable, which we have some idea of, are actually telling us where, giving us, if you will, what the force of gravity. And so, if that were not true, we wouldn't have gravity. How do we test that? Well, it's difficult, but I believe it is ultimately testable, so that we can, in other words, that
So you're
curvature
saying, so
is
you're saying
apparent
you
and
can
real. We
test
should be able
whether
to
the
measure it.
universe is finite or not?
Yeah, I believe. Well, what we can see locally here would be actual curvature of the universe, which I believe, that is to say, if we were to, if we had a triangle large enough, and then we could get to all 3 points in a triangle, we would notice that the degrees in that triangle were less than 180, or excuse me, more than 180 degrees. Just like the 3 points on a globe, if you were to measure the angle going from those 3 points on a globe, you would see that they were more than 180 degrees, and that is measurable, provided that we can get a triangle large enough. So that's the problem. But so yeah, I believe, and to that extent, that curvature, if you will, that's a two-dimensional example, is measurable, and it's present, and it is something local here that we can actually have. And can we measure it? I believe we can. It's extremely small, but it's responsible for gravity. So that's my personal feeling, and I know that's beyond where you're trying to go, but it does have some effect, some determination. Your worldview, if you will, your whole picture of what's going on in the universe is going to be determined by, number one, is the universe infinite or finite in either extent or in time. Those questions are going to be, let's put it this way, I need to know where a person stands with respect to those questions before I can kind of get where they're going in terms of their understanding of cosmology. Those are those deep foundational things that I think some people just kind of assume and don't even talk about. Just assume that doesn't everybody know that the universe is infinite, and then all their theories are based on that, and they're not they're not acknowledging that's there, that foundational belief system, if you will, about how the universe
Well,
is.
this raises the issue, though, as far as I could see, is how you going to test that. I mean, the way I see what we have now is we have a theory. They're applying a theory, which is this general relativity, and the way it works is Einstein had this general relativity theory, and then um, about about the same time, or actually before, Slipper had discovered the um, redshift of nebula. They didn't really even know that they were external galaxies in those days. And then later, when in the 1920s, Hubble was able to prove that the galaxies were actually outside of the Milky Way. And that was a big step forward. And um, so then that said that these galaxies, which were outside the Milky Way, are expanding. And then Hubble was able to show that the further away they are, the faster they're moving away from us. I'm sorry, did I say expanding? I mean, moving with a velocity.
Mm-hmm.
So then when the Friedman models looked like they predicted something similar to that, that the universe was expanding, then they sort of latched onto that. But to me, that's just kind of could be a coincidence.
Sure. I'm not.
And so to sort of say that you can describe the universe by a simple equation strikes me as kind of arrogant. Maybe that's not the right word, but the procedure that they're doing now is they have a theory and then they look for evidence that supports that theory. And
Well, I
yeah,
don't think
okay,
that in
so
and of itself is bad.
uh,
I mean, what else can you do? I mean, we come up with some kind of a model, we test the model, and then we
yeah, but
change.
that doesn't necessarily mean it's true.
Agreed. Yeah, I'm not arguing with you.
And
The
I think
problem,
this
though, is when
the
they
Big
find,
Bang Theory, though, of course, has the problem that it has an origin in time. If you go backwards, you have an origin in time. So if you have an origin in time, that sort of implies finiteness, wouldn't you think?
I would say so. Yeah.
So, but is that really a valid conclusion? So you would have to assume that you could prove the universe is expanding. in order to say that you have to have some kind of an origin in time. So that would be one thing. Can you
Oh,
prove the
I don't
universe is
see. I
expanding?
don't go with that whole expanding thing at all myself. The question I always come back to, and I don't know. I've tried to get this through to people, and I don't seem to be able to succeed. So I'll give it a stab. But basically, the question I keep coming back to is what does it even mean? Forget asking whether we think the universe is expanding or not. I want to ask a more basic question and say, what would that even mean? If the universe is finite, with respect to what is it expanding, and how could we even tell? The example is like a balloon. You got dots on a balloon and you expand the balloon. Well, the dots expand as the balloon expands. If you're one of those dots, you're getting larger with the universe. You can't even tell. You know, the only way you can tell is the thickness of the balloon, but there is no thickness because we're not living in that extra dimension of thickness. So it's meaningless. The only way to tell, so it's not even the only real relevant question, let's put it this way, the relevant question is expansion of the universe is completely identical with contraction of all the matter within it. So in other words, if I took my balloon and rather than the dots getting bigger as I expanded, the dots stayed the same size, that I can measure because now the little, you know, it's the dots relative to the universe that matter, not the relative size doesn't matter. We can't tell that. I'm sorry, the absolute size we can't tell. It's only the relative size of the dots to the balloon. So the objects, the matter in the universe to the universe, that we can measure. That's why I keep saying the size of the particle relative to the size of the universe. That's important. That's a number we can measure. I believe that's going to be the same as Dirac's constant, which I call it Dirac's constant. But the absolute size is not measurable. We have to measure something relative to something else. So what does it mean to say the universe is expanding? To me, it's a totally meaningless statement.
Hello,
Yeah.
Mr. Volk. This is Alex Mayer.
Hi, Alex.
Hi. So I'm very, very pleased. Thank you very much, by the way, for sponsoring this or for creating this meeting. Sure. I think this is my first time joining such a meeting or using Fuse.
Okay.
And I think thank you. Did I sent a text? Did everybody get that? Did that work?
Everybody, the chat is this is a new system for all of us.
Yeah.
So Alex, okay, it says hi all. This is Alex.
Yeah.
Alex Meyer.
So that's me.
I see it. Okay.
Okay. So actually, all of the things that have been discussed so far, and I missed out. I had a little problem with my browser, so I missed about a few minutes when I had to relaunch. So I'm a theoretical physicist and cosmologist, and I can assure you that you are correct. And all the information, it's actually online. And
correct about what?
Well, the universe is not, okay. It's a difficult thing to say without, but the slides that are online right now, pretty much, I think it's a pretty erudite audience here. I heard it's mostly like engineers and people who have a technical background. Mm-hmm. Just to give a quick background, so cosmology was created with the creation of the Einstein field equations in 1915, 1916. Mm-hmm. And it was really launched in 19.
Well, there were cosmologies before that, in the sense.
Well, I would say there were
cosmogonies
because there was no tool. Because without the mathematics, without the field equations, there was no reliable tool in which to study the true issue of cosmology. So arguably, cosmology began in 1917 with the two papers by Einstein and then De Sitter. De Sitter was an astronomer, and unusual for an astronomer. He was a brilliant mathematician, very, very good mathematician. And this is, remember,
that is unusual for an astronomer, but okay.
Yes, he truly was. He was one of the few people in the world actually who could work with the field equations very, very easily. And it turns out that in 1917, And it's mentioned, of course, in Hubble's, at the last paragraph of Hubble's paper, he says, well, maybe this is the de Sitter effect, and we have to think about curvature. Now, the de Sitter effect is very well, de Sitter found a solution to the field equations that includes a cosine term in the time. And it was discarded for a number of reasons. And then, basically the time term, it says cosine, little r is the distance from you. It's the distance that the telescope is seeing. Big R is the radius of the universe. So you can think of just like sort of the Earth. You could think there's this effective radius, and so if you want to go all the way around the universe, it's 2 pi r, big R. So he's got this term cosine r, little r over r times the time. And so if you think about that, if everybody can sort of follow that, you might want to scribble this down on a piece of paper. So the time is the cosine of your distance that you're looking divided by the radius of the universe, which is sort of, you just draw a one-dimensional, if you want to call it a one-dimensional circle. And what that says is that based on distance alone, right, so there's no motion, the time is slowing down, and it's just like velocity. Now that's absolutely for sure. Everybody, I'm sure that everybody here that I'm looking at, Hunt and Glenn and Franklin and everybody else, understands that the relativistic gamma term, that as something goes faster and faster towards the speed of light, the clock slows down. Well, de Sitter's cosine term basically said, guess what? According to the field equations, as you go farther and farther away out to what? To pi over 2, right? So 90 degrees, because at r is equal to pi over 2. The little r is pi over 2 divided by r, and you're going to basically the cosine of that of pi over 2 is going to be 0. So the clock slows down. Now that was thrown away. It turns out, and you'll see that the Sloan Digital Sky Survey data proves beyond a shadow of a doubt, it's over at this point. It's completely over. You'll see it. The data is unbelievable. It's unbelievable because there's 2 million data points. Now I'm going to tell you guys, this is not new information, and the people at the top, I was kicked out of Stanford, and then I was kicked out of Berkeley. I was physically assaulted by an American professor at Cambridge. Following these events, this material, it's like right out of the movie.
You didn't tell us why. You just told us that.
Because the information that you can all download, if you Google Alex Mayer, that's all you need to do, because there's plenty of people who know about this. It's just not public yet. So if you Google Alex Mayer, I'm either the first or second, or something. It depends. Usually I'm the first hit. So it depends what country you're Googling from. And then you'll see it says slides. Now, the slide presentation that I put out in January, it's huge. It's a very comprehensive. It turns out that there's a very small, insignificant mathematical error in one of the formulas, which I'm going to fix, but that it's not terribly relevant. But what you'll see there is it's basically over. And it turns out, and one of the things that's not in that presentation is the connection to de Sitter.
You're going a little fast for me. What's over?
Okay. The Big Bang.
I think what
theory.
he's saying, Greg, is that the redshift is due to a time change.
Correct. It is a relativistic effect. It's called the de Sitter effect. And even Hubble, who basically, there's this whole huge, beautiful history about like what really happened, that the Big Bang theory was invented. It was a concocted idea by Lemaitre, the Catholic priest, and we discovered 10 years, because I did my homework, because I do the history, I do the math, I do everything. So
Alex, can I ask you a question? I know you're talking about, I don't want to interrupt this. I want
to. Go ahead.
Do you have a copy of de Sitter's book? I have a copy of de Sitter's book. Is this explained in his book?
No, because he abandoned that idea, because he eventually got on board with the expanding universe.
Oh, okay. This isn't really described in his book.
Go to NASA. Okay, probably you're all familiar with the astrophysical data system. NASA. If you Google NASA ADS,
I know that.
Astrophysical data system, and if you go and you just Google de Sitter and you can put in 1917. You will see it's called his third paper, 1917 third paper, And I actually, in the new stuff that's going to come out in a couple of weeks, that's going to replace, I'm chopping up that slide presentation. That's like 400 slides, and I'm chopping it up into like 3 or 4 pieces. And I'm doing a much better job on the de Sitter, on the connection to de Sitter, because I really didn't cover it at all, really, in those first 400, that first slide presentation, which, so it's not in his book because he abandoned it because there were, and this is where it gets really cool. And I'll tell you something that's not in the current slides. The first reason it was abandoned is because it requires the net energy density of the universe to be 0. Rho equals 0, which didn't make sense to anybody. It was like it was sort of the empty universe. It was sort of like a
yeah, I'm familiar with that. The empty universe of de Sitter.
Yeah, but it's the empty, it was the empty static universe. Okay,
right.
And that was, and then that just became like, and then the empty expanding universe became, without the cosine term, became some sort of fiducial model, where that where basically omega equals 0. But now it turns out, because of this, you'll see that the time, because if you think, here's the model that's so easy. Draw a circle on a piece of paper and think of that as the null geodesic, or a cosmological geodesic, and that's space. That's it's one dimension of space, even though it's a circle. Remember, the circle is in space-time. So it's one dimension, because any little dr on that represents, one dimension in space locally. And here's the cool part. So remember that little dr, well, according to Minkowski, and this is called Einstein's strong equivalence principle, which basically says that the universe is the same everywhere, then the time coordinate, right? Because the space is local, the free fall is the same everywhere. The time coordinate is the local vertical. So that's the radial. So you see that? And that's where the cosine term comes in. Because as you go around the circle, the little arrow, which is the local vertical, which is basically the local radius, that's the local time coordinate. And they're not parallel and they're related by what? The cosine. Because, right, it's the dot product. Any engineer is familiar with the dot product. It's basically saying, okay, since your time coordinate is not pointing in the same direction as my time coordinate, are you there?
Hello?
Yeah.
Okay, because
I'm looking at your slides as you're talking here. I got your just 22 slides.
Yeah,
well, Alex,
that's
I
the intro.
want to say something here, is that we don't want to spend a whole lot of time on this. We want to let other people have a chance.
Yes, of course.
Well, I'll tell you what we ought to do here. Why don't we schedule you to give us a talk one of these days?
I would love to do that.
Rather than take, like Carrie says, this is meant to be a discussion, kind of for everybody to get their 2 cents in. But let me just clarify. Just before
I like what you're saying, Alex, because I've felt for a long time that that time was changing and not space.
Correct. Your intuition, and you're not alone, but no one just could quite put it all together. And I just got lucky. And here's the interesting thing: that the top people, of course I did the normal thing. I went to the top people in the world, and I showed them this. And of course they're not stupid, And then this is it from a grad student quote: overheard at Harvard. It's 2 professors at night talking to each other. And then this guy was like, what the hell? Of course Mayer is correct, but he can be correct in 20 years. And that was 5 years ago. Of course,
got 15 more to go.
Yeah, because they don't want it, because basically this thing is but basically they're trying to push it off to the young generation. They want these poor kids, these poor graduate students, to just struggle in the bullshit for another 10 or 15, 20 years. Then these guys will, basically retire and die off, and then they'll just push it off. They're and which is really, really unethical.
So the politics of the science.
Correct.
There's
Anyway,
Okay,
I'm
a,
going to
so
sign off because
but
I've
well,
spent too
hold
much
on.
time.
I want to just to clarify a couple things. Okay, so when you said you were kicked out of Stanford, you were kicked out of all these places. So
Yes.
I want to clarify exactly what that meant. So you were a student there, or
I started off, I was by the way, there's all this stuff on the internet. I mean, there's a record of this. So I was what's called a visiting scholar at Stanford. And it was
okay,
kind of interesting. I was actually working in the Valley. I was working in Silicon Valley, and I would commute past Stanford. And since I had a strong connection through my company with Stanford, I went to this physics department and I said, I do physics, and right now I'm not an academic. I'm actually working, in the Valley, but I basically want to spend my evenings at Stanford working. And they said, hey, that's fantastic. Come on, here, we'll give you a one. And I still, of course, I have all the records. I have my ID. So they said, yeah, we'll give you a 1-year visiting scholar. You can stay at Stanford. You can use the facilities and whatever. And of course, along with that came a website. So my website was stanford.edu, tilde A Mayer. That was and I published, and this is going back a long time. This is 10 years ago when I started the research, and the writing was on the wall. I wasn't anywhere near where I just because now it's over. It's just, this was DR7, Data Release 7 of Sloan Digital Sky Survey. I didn't have all the math, but I had, but what I originally published, because I'm an expert in database. I'm really good at mining. That's the problem. A lot of people they can't combine all. You need to be a database expert. You need to know some math. You need to know some physics, and you need to know some astrophysics. And I kind of put all that in one big ball. And anyway, when I published the initial analysis, that basically it was scary. Meaning, if you were supporting the Big Bang, then it looked like, wow, this looks scary, because if this is right, then okay, and that's what got me. And people noticed on the internet, was somebody published something about it on something called Slashdot, and there was a lot of attention, and Stanford, and that's what raised the red flag, because Stanford, people were saying, who's this guy at Stanford who's challenging the status quo? And it was overnight, like a cosmologist a cosmologist, and I didn't even know, because I was completely politically illiterate.
Alex,
yeah.
do you have an email? I can send you my model of the universe, which is
Yeah, you know what? At this point, I'm not interested in other people's models, because they just, frankly, I'm not being. If you go through the slides, it's over. And the work that I do, and what's so interesting is it dates back 100 years. I mean, De Sitter was a better mathematician than I am, I would say.
Yeah, you fit right here. Nobody reads anybody's theory. So that's really...
No, because I'm not. You know what? It's almost a little bit. I'm not here to. Science is not a marketing job. It's an education job.
That's right.
It speaks for itself.
I have a question for you. Okay, I as you were speaking, I was trying to find this paper, and I can't find it in your slide present. You said De Sitter's third paper in 1917.
Yeah, you can go to ADS.
I did. I could not find that. So
what I'll do is, you know what I'll do? I'm going to sign off, because I've spent way too much time. Thank you so much for listening. I mean, for being so hospitable. I'm going to turn my mic off. And I will send a couple of these text messages with some information for you guys, okay? And then why don't we? I'll give my email address. Okay, here's my email address for everybody you want, or I'll send it. But it's just amayer, AMAYER @alum ALUM.MIT.edu. So, and I'll put that in.
I'm kind of slow. AMEYER is as far as I got.
I'll text. It's A Mayer. I'll text it right here. Let me just use this little text feature. Okay, hang on. It's
sounds
A
good.
Mayer.
All right. Well, we can open it up to discussion. So, but what I get out of it is there's a cosine term in De Sitter's 1917 paper that's a magic key to understanding.
Correct.
And that's about as much as I was able to glean out of all that. But I'm interested in that, so we'll see where it goes.
Okay.
And Harry, did you want to say more? I'm happy to step aside.
I think it's interesting. Um, I hadn't thought about De Sitter, and I've heard about what he's talking about. Um, I was aware of it, but it's kind of far down in the noise. It's one of those historical notes that you don't really pay. You know about, but you don't really pursue, and that's kind of a problem with establishment science, which is they focus on a particular pet theory, and you have all these other theories that have been proposed and nobody's working on them. And so, because the majority theory has no competition, it basically uh, maintains itself because it's got no competition.
Right. Okay. I am about to send, let's see here, join meeting. All right, so here's the De Sitter paper right here. I just sent the, that's the 1917 monthly notices of the Royal Astronomical Society, the third
Got
paper.
it. Thank you very much.
So that paper gets a little heavy on the math, but it's if I remember correctly, it's equations. He shows it's like 8A, 8B. One is Einstein's static solution, and then he does the cosine work, and he nailed it. He just nailed it.
You said the equation numbers are 8A and
Yeah,
8B, the significant equations?
I believe so, yes.
Okay, I'm trying to get the PDF version here, and I'm not getting anywhere. What's the problem? Well,
It is.
Oh, here we go. I got it. Okay, 26 pages, yeah? Einstein's theory of gravitation?
Yeah.
November 1917. And you said equations
Correct.
8A and B are the key equations, yeah?
Yeah, 8A is Einstein's static equation, and
Yeah, I see it.
is the one with the cosine term, and it's squared.
No, 8A does not have a cosine term in it. It looks just like a coordinate transformation for spherical coordinates to me. Got a sine squared term.
And 8B's got the cosine term.
There is no 8. Oh, there's 8B. Yeah, okay. Cosine squared.
Well, that's because it's a metric. The metric is squared. It's sort of like A squared plus B squared equals C squared,
gotcha.
right?
Okay. That's the extra term. Or that I
right,
see in place
square
of.
root is cosine R over R C.
Okay, so the difference between 8A and 8B is that there's a cosine squared R over R, the little r over big R term multiplied by the C squared dt squared.
Correct, and remember the C squared just converts time into space. So that we're doing, it's basically a units conversion.
Yeah, I understand. Okay, so that's that's the magic trail right there. That cosine.
It is, and it's so strange that they have. I mean, there it is. It's right there, and the data, of course, follow the data. You'll see the longitudinal sky survey data is everybody. We this paradigm thing and expanding in the linear relation system is highly nonlinear. It's cosine, right? It's but if you go to SDSS data and you look at a million galaxies, and it's spectacular. It's just spectacular. So anyway, I'm going to sign on. And you have my email address. I'm actually currently working in Krakow, Poland, which is where Copernicus was a professor. And there's growing interest in a very small minority of real people in this work, and I've given lectures.
Fake people here. Plenty of that.
So I think this is going to take off pretty rapidly. And it's kind of interesting to set up this meeting. It's really kind of fortuitous.
That's good. Thank you.
Okay,
Harry, take it over. I'll disappear myself.
We're getting a pretty bad echo.
Yeah, real bad. Who is?
That's because everybody.
I think it's John Walls.
See who's guilty. All right. Oh, there. Whoever it was, it went away. So thank you, whoever just muted yourself. That's fixed it. Okay, Harry, you're back on.
Oh, I'm back on. Okay, is there anybody else who wants to make some comments?
Yes, I would like to make comments about Hubble Discovery that you mentioned before. And you said that Hubble...
Okay, speak up. What's your name?
My name is Herman.
Okay, Herman, speak up.
I would like to talk about Hubble discovery and its general perception that Hubble discovered receding. Actually, and it goes from one textbook to another, and indeed Hubble discovered the dependency between redshift and distance, and receding is just interpretation. So Hubble, first he was interpreting this as a receding, but then few years later he changed his mind, and to the rest of his life he was not believing in receding. So receding really is not a discovery by Hubble here.
Okay, let's go over this.
Believe in it.
Okay, I've heard this before.
Thank you.
I've heard this before, Herman. I have a copy of Hubble's book. I don't know that he talks about this in his book. This is something that's in later papers, from what I gather. And I'm not sure exactly what the reference is. Is this not correct? I don't think it's in his book.
It's the paper done by ISIS recently.
I can't hear you.
My reference is the paper by ISIS, a Brazilian scientist who made the analysis of how it works and his beliefs over his life. It's like Hubble versus Sandage, something like that. Sounds something like this.
Okay. I've had a dispute with a lot of people. Al McDowell. A lot of people. The books talk about the Hubble law. They use what's called the Hubble law, which is, they talk about it as a distance velocity relation. They call it the distance velocity relation. And they've that's what was actually, the experimental evidence is actually a distance redshift relation. And
yes.
It depends on what your interpretation of the redshift is. Now, as I maintain, as what Alex Mayer just said, he said the redshift could be caused by a change in time. The current establishment of science asserts that the universe is expanding, and it's the expansion of the universe which causes that redshift. And so the farther away a galaxy is, the more the redshift, the expansion effect changes the redshift, and so you get a linear relation. But that, again, my point is that's an interpretation. So we don't, so the question is, and I think Alex brought this point up clearly, the facts of cosmology are, this is one of the big facts. I think there are two big facts of cosmology. There's the Hubble relation, the Hubble law relation, which is distance redshift, and then there's the cosmic microwave background radiation. Those seem to be the two real basic facts that seem to be well established, that any cosmology or interpretation of the universe has to sort of deal with. I don't know that we know what redshift is. And so you can argue, that's an issue. And then, of course, the other issue, which we haven't talked about yet, which is the cosmic microwave background radiation. And what is the cause of that? What the modern Big Bang has done is kind of clever in that there were Wegener, who is a German fellow, predicted a temperature of 2.8 K in 1933, and there were 2.8 K. I mean, he nailed 2.8 K in 1933 before there was any concept of a hot Big Bang theory. So you don't need, as far as I can see, I don't see why you need to have a hot Big Bang to explain the 2.8 K that's observed. But they take the 2.8 K cosmic microwave background and say, oh, that proves the Big Bang. To me, that's not convincing. So we have the question of the redshift. Is that really interpreted correctly as being due to an expansion of space or of the universe? And the second is the cosmic microwave background radiation being correctly interpreted as due to the quote hot Big Bang. I don't really think in either of the two cases the interpretation is correct.
Yeah, just to speaking of Reginer, he not only predicted, but he actually measured this temperature using stratosphere balloon in 30s, way before the official discovery of cosmic microwave radiation.
Isn't that kind of interesting how they ignore that?
Yes, yes.
Do we have any other comments, Herman? Or anybody else want to comment?
Can I interject something?
Who are you?
Michael.
Michael.
Yes, I keep getting notices from the Holster saying the next meeting will include this or that ether theory, but everything stays strictly quantum empiricism, earthbound quantum empirical data. I mean, it's getting so heavy that, an ether theorist like me feels really on the outside. And ether theory could put a whole different spin on these questions of cosmology, such as first cause origin and presence of anomalous stellar evidence and so on. I mean, it's a whole different ballgame, and we never even hear about it. We just, I don't know. I mean, I guess it's up to you.
Well, there is, I'm not sure when David has this schedule, but we have the plan is to talk about that particular subject at the next open discussion. And I'm not sure when that's scheduled for, whether it's next week or what. I haven't looked at the schedule, but that's in the plan. There were three things. We were going to talk about special relativity, cosmology, and ether theories. And the difficulty with bringing an ether theory is, as you well know, that really is a hot button for the establishment. I mean, that's something they absolutely don't want to talk about, and so it's kind of a hot button for sure.
Can I interject now?
Sure.
This is John Soul. Hi. This last month, I'm really excited about what Alex had input, and I'm
Speak up.
Is my voice too low? Is that any better?
Yeah, make sure you talk directly into the microphone.
Okay, the mic's on the headphone, so.
For what it's worth, John, I hear you fine. I think Harry's volume is just, he's not hearing anybody well, so.
Okay, all right. All right, so I was really almost set off by Greg's comment that time expansion of the universe is meaningless. In the model, I just put in the chat window a link to a paper that I just published at the Fundamental Questions Institute essay contest. And in there, while I was writing the paper, the ideas in my head were getting clearer and clearer. And I saw quantum gravity form in my head, and I managed to get it on paper. That's on page 6. But this whole idea of what is time, and in my model, I've discovered that the time itself is the expansion of the universe. So even if you had a universe with no matter, ordinary matter at all in it, this model has a concept of what time is. It also has an absolute reference frame based on this three-dimensional, 3D surface expanding within a 4D volume of a cosmic onion. And probably remember this from the 2013 presentation. I had about 90 minutes of material and 30 minutes to present, so it didn't make a big splash then, but now with some of the math worked out a little bit more, and this quantum gravity added to the mix, I think it becomes really interesting. Essentially, what became very, very clear is that Planck ticks per second increases with the age of the universe. It's just continually more Planck ticks per second. So depending upon how deep we are in a gravity well, that determines the rate at which that Planck ticks per second increases. The deeper you are in a gravity well, the slower that happens. And so, although it's true that the forces of electromagnetism, greatly overpower gravity, it doesn't stop expansion. And so, in my model, the space-time dent that the Earth creates in what I call the space now manifold is steepest at the surface of the planet, and it goes down to kind of a crater shape in the center of the planet. So the center, literally the atoms in the center of the planet expands ever so slightly faster than the exterior, and so that causes the Earth to split and have the big cracks of the ocean bottoms. Anyhow, so far I've only had one person look at my paper, and they were I felt kind of low on the perceptive totem pole, and he rated it a number 3, which is like F minus. So my chances of anybody else reading the paper have now gone down to 0, because there's hundreds of 100 other papers out there that some of them are, by the way, are very excellent. You got to check out the guy who wrote on. There's too many of them to list. Anyhow, check out the list. If you guys are at that level of math of some of the papers, you'll really enjoy some of the contest participants.
Oh, you're fading out now.
Okay, sorry.
What was your name again?
John, last name W-S-O-L.
All right, John. Thank you.
All right, I'm going to shut off my mic and let other people get some input going here.
Harry, this is Nick.
Nick, speak up.
You remember the 120-page monograph that I sent to you? See Johann Masrelais?
Did you send that? I guess I missed that.
Oh, okay. It seemed to me that he was saying pretty much the same thing as John just was talking about, except he was taking it from the opposite perspective. He was saying that the expansion of the universe is what drives time. I wanted to make a couple of comments earlier.
I'm having trouble hearing you.
Earlier you said, Harry, that mainstream has their theory about the Big Bang, and then they go out and look for evidence and try to fit the evidence to prove the Big Bang. And Greg said, well, there's nothing wrong about that, and I agree with that. However, let me give 2 examples where they've gone too far. First was the creation of inflation, where they said that the universe expanded by a factor of at least 10 to the 78th power in a period of time that is less than 10 to the minus 32nd. In other words, an unbelievable expansion in an unbelievably short time. And the other thing is, the Big Bang is dependent upon general relativity, but because the data doesn't match general relativity for, say, the rotation of the universes, that necessitated the mainstream to fill the universe with 96% fudge factor, namely dark matter and dark energy. So I just wanted to get that point out.
Well, I can't disagree with that. My point about it is I feel that cosmology isn't really science in the sense that of 19th century science, where science was you went and you studied a phenomenon, the Faraday approach, you did experiments, and in the case of cosmology, you would go out and you'd look with your telescope and you'd measure things. And then once you'd measured all these things and made a bunch of measurements, then you would try to explain them based on that would be inductive science. The current popular approach is to create a theory and then look for evidence that supports that theory. And I don't think in the case of cosmology, that particular approach works very well. That's what I'm saying. Because a lot of what we see doesn't fit into the theory very well, which was what you're saying.
Right. They have to bend
Okay.
the theory or augment the theory so much to bridge the gap between the base theory and the empirical data. That's where they go wrong.
Anybody else want to comment?
Well,
Yeah.
well, perhaps I could briefly come in here, Harry.
There's Ian. All right.
Ian,
Welcome,
yeah.
Ian.
Thank you very much, Harry. Been absent for a little while, although listening and following the emails. Many of the points that we have been discussing, and particularly at the beginning, are really philosophical. And of course, I do take Greg's point that one's approach is largely dependent on these philosophical preconceptions. But I was interested in how he also mentioned almost a type of a curvature in space, I think, or maybe I don't know about talking about a finite universe, and Alex's very interesting contributions, which will require some significant study and perhaps, as has been suggested, a presentation, seems to a certain extent to be doing what Nick has just elucidated there. In other words, looking at general relativity and saying, well, it's not quite correct the way they put it in, and let's put a cosine term in and so on, and we'll find that time is actually dilating, and that's causing the system. Whereas, for me, to a certain extent, I'm more classical actually than any of that, I think. To me, the universe, by definition, is everything. So, philosophically, a finite universe just causes me problems, because what's outside that? Well, I say, anything outside that must be part of the universe as well. And, you talked about the ether there a moment ago. To me, if one, it looks empirically at the medium, the ostensible medium for the propagation of electromagnetic radiation, one can find, the well-known electric permittivity and the magnetic permeability. But one can also find the very, very small, almost zero, but very, very small conductivity. And if one puts that into the partial differential equations and so on, one actually gets a dissipation in the ether over vast cosmic distances. And if you like, this is basically a sort of a tired light type system. So to me, that's really what's causing the redshift. And I totally Herman, to a certain extent, stole some of my thunder, because I was going to say something very similar to him, and you've said it as well, Harry, about it being ascribed to what's his name? Just lost my train now. Well, Hubble in 1929, because basically all he was doing is he was saying, look, there is a relationship. I've measured all these distances with these Cepheid variables and the galaxies and so on, and I'm finding that the redshift seems to be roughly proportional to it. Now, if that is due to expansion, these are the consequences. But if it's not, if it's due to a Zwicky type tired light, these are the consequences. Well, and I don't know, I'm sitting on the fence. And unfortunately, whenever Hubble's name is raised, we think of the velocity redshift dependence. And in a similar way, whenever, the sort of E equals mc squared, we think of Einstein, and Einstein really is not responsible for that at all in its origins. So those are just a few points I'd like to raise in relation to the discussion, but it's most interesting. Thank you.
Hi, can I interject here?
Thank you. Go ahead.
Yeah, in my paper, I got almost 2 paragraphs. This is John Soul.
What's your name?
John Soul.
John?
I've activated my camera. Is there a way to
I don't see you on here. That's why I'm asking.
John? Oh, W-S-O-L. W-S-O-L.
All right, go on.
John. Okay. I've activated my camera if anybody's interested. In there, I go through great lengths to draw a distinction between Doppler effect, which is instantaneous, that while the wave is being induced in the medium is carrying that wave at the rate that the medium carries light. Okay, it's an entirely different phenomenon to say that the galaxy is at a particular position in space-time, and we're here at a different position, and we're waiting for that light to arrive. The entire duration of its journey, space is expanding, clock rates are slowing down at the same exact rate, so the speed of light is constant. Literally, I'm talking about the metric by which we measure distance and the metric by which we measure time slows the entire duration of the journey. So by the time it arrives in our here and now reference frame, we see what we perceive as a redshift, but it's not from Doppler at all. Well, Doppler can be mixed in if the galaxy, say, is spinning, and we're seeing an edge on. Of course, that's added into the mix, and as light exits the gravity well of a galaxy or a massive star, it's stretched by gravitational redshift, and then as it enters our galaxy, we're seeing some lensing effect by the shape of our Milky Way galaxy. Is kind of like one of the distortions of how we see the rest of the universe, depending upon if we're looking perpendicular to the plane of the galaxy versus looking across just above the galactic halo. That's going to have a distortion effect on how we view the rest of the universe. I'm going to mute my mic now. I think.
Okay, thank you, John. Any comments on that? Does anybody have any comments about the cosmic microwave background or the redshift or the Hubble law relation? I'd like to move on to another little topic here. I don't know that a lot of people are going to be interested in this, but I am. Any questions or comments?
Yeah. On the last page of my paper, I show one of the cosmic microwave
Is this John?
images. Yeah, this is John again. And in that image, it shows some anomalies, very strong anomalies. And in the text, I describe that as when we look back into time, we're looking into a hyperspherical universe. And so as we look deeper and deeper in, we're looking into space that is more and more curved at a time when clock rates were faster and faster relative to our ever slowing clock rates. So it's distorting both our perceptions of space and time, because it magnifies the space of the distant past, and it literally magnifies clock rates. And so some of the things that have been observed is this thing called dark flow, and that's because the light curves that we see arriving at a here and now reference frame are a spiral staircase at the Planck level of photons that are traveling across the cosmos, across space and time. And those photons, are slowing down. But it's causing this magnification effect. And so one of the things that we would see is on the cosmic microwave background image, we would see like a pole that is either emerging or converging to a point, and that when it emerges, it would be like a ring around the cosmic microwave background image that would slowly morph and work its way around the sphere. And so that's something I think is showing up in these anomalous images, and if we keep on watching, we'll see it morph even more. So that Planck satellite, I hope it's got a long lifetime.
Okay, well, that's interesting.
Harry,
I'm tempted to talk a little bit about that, but I hear somebody else wants to get in.
Harry, this is Jerry Hinechek.
Jerry. Speak up, Jerry.
Yeah, I have derived a formula which ties the Hubble constant to cosmic background radiation. And I have published that, and this kind of relationship, from Hubble constant, you can calculate cosmic background radiation and vice versa. This kind of relationship is only possible in a finite universe with infinite time. So, I have published that in numerous places.
Okay, Jerry, let me ask you this. What do you get for the value of the Hubble constant?
68.
That's pretty low.
Yeah, it's actually recently measured value is 67.9. And that comes exactly from the temperature, which is 2.7 something 55, I forgot.
Okay, so that's comfortably within the oldest stars are younger than the age of the universe, right?
No. Yeah, I don't believe in the Big Bang. I'm sorry. If you missed that, I say that the universe is finite. Of course, the galaxies are receding, but when they come to the end of the universe, they explode and generate the GRBs. So you have another parameter which is to explain, which is GRBs, temperature, Hubble constant. So and the velocity.
What's the GRB?
GRB, gamma ray bursts.
That's what I thought.
Which are detected, about one every day or so, and this is well documented. Supernova, and all that. I have even presented this kind of theory at these meetings here, but for some reason nobody pays attention to it. So I don't know.
Now, is this described in that physics essay paper that you got published recently?
It is in physics essays, and also for some reason that link disappeared there. I think the anti-Einstein defamation leak is probably it's blocking it, or somebody is blocking it. But I have also put some of the papers on the Vixra website, so you can download it and read it.
Okay. I think I sent out the physics essay paper with a number of the other papers on cosmology. I don't think everybody got that, but I took a look at that paper. Thank you.
All right.
Anybody else? Actually, my interest.
This is Alex.
Go ahead, Alex.
So your questions were about the cosmic microwave background.
Well, we were talking about that. I brought that up as an issue because, as I said, there are two issues. I could be wrong. You can correct me on this, but to me, it seems like there are two observational facts that have to be explained. One is the redshift velocity relation, and the other is the cosmic microwave background. You have to deal with both of those if you're going to have a theory of cosmology.
Correct. So the first thing is that once we prove with the data that the redshift isn't the redshift distance relationship is nonlinear. As soon as that's an established fact, then expansion goes away, right? Because expansion requires that it double the,
Right.
for
Now, I have
as
seen
long
people
as
who
the
claim that it's quadratic.
well, it turns out it's a cosine term. I mean, in other words, now remember, you can't, you just, it's fun. I mean, science is fun and it's really interesting to play with some ideas. I mean, and I really respect that. It's an old, remember that Isaac Newton himself put more effort into alchemy than he did into science, which is pretty amazing. So I actually really respect people for making an effort and coming up with ideas and like many people do. But in this case, we really have to stick with general relativity because we know that it works. And then just like it was beautiful, like the Newton's equations. I mean, we're going to use them forever for normal everyday life. But of course, the one thing that Newton didn't get was the limiting speed of light, right? And God bless him. I mean, it was 300 years ago. Of course, he couldn't. But so remember what Einstein did. He did not trample all over Newton. He didn't say, "Oh, Newton's an idiot. He didn't know what he was talking about." No, he said, "Oh, we have to add this crazy idea that the speed of light is constant for all observers." And then once you and that's all he did really. It's all he did. He said the speed and the Michelson-Morley experiment and all that. And then relativity comes up. And what's so interesting is, of course, we know for a fact, I mean, we use GPS, we have linear accelerators. We know that Newton's equations of motion are nonsensical when you're talking about relativistic velocities, right? If you plug in, the speed of light, you can't design anything that way because it just doesn't work, right? Because you need the relativistic equations of motion. And here's the cool part. So the one thing that the little mistake that Einstein made, which is he didn't, and it was really strange because Minkowski did. Remember, Minkowski was Einstein's math professor at the ETH. And remember, he's the guy who called Einstein a lazy dog, which was funny. Now, the reason almost nobody knows Minkowski, who was a bigger genius than Einstein, he wasn't as he didn't think outside. He wasn't as radical as Einstein. But remember that Einstein, this upstart patent clerk, publishes this incredible paper, right? By the way, there was no peer review back then. Thank God. Max Planck was the associate editor of the Annalen Physik, right? He gets this paper from this complete nobody who he's not a professor or anything. There is no peer review. Planck was a good guy. He was an honest, real physicist. So he reads the paper and goes, "Oh my God," immediately publishes it and immediately starts lecturing about it. Unlike the guy at Cambridge.
I think we're all familiar with this, Alex. Can we get to the issue of what you?
All right. So the thing is as soon as the universe is not expanding, okay, then you don't have a Big Bang, and then you have to reinterpret the cosmic microwave background.
All right, but here's the question.
What's the question?
You're saying if the redshift distance relationship is not linear, then that would do what?
Then the universe is not expanding.
Okay.
Period. That's it. There's no expansion.
But the problem, it seems to me, is what they're doing is they're fudging the redshift, the data, to make it fit to a particular model. So when an astronomer takes these redshift distance data, he fits it back into a particular cosmological model and then publishes the data that's corrected based on his cosmological model. Isn't that what they're doing?
Yes. As a matter of fact, it's getting so crazy because in 2010, I mean,
You're fading out.
Hello, can you hear me?
Yeah.
Okay. So Perlmutter et al. Got the Nobel Prize. I mean, it's a joke. They know, by the way, they know that it's bullshit. Pardon my French. You're absolutely correct. The data that's one of the big political issues right now, because these people, we're talking about people who got the Nobel Prize. They falsified their data to an extent that is mind-blowing. I mean, it's not even close. So the data, and that's the thing, the physicists believed in it. It's basically the same thing as Madoff. I mean, Madoff, you know, I mean, no, they published, here these professionals. Madoff was like a former president of the SEC or something, or he was some very important.
Yeah, we know about that. Okay,
so the thing is that people believe the data.
To keep you on track, what you were saying is we should be looking at the problem is that there's so many fudge factors that you go into when you sort of try to say what is the actual law of redshift versus distance. There's so many fudge factors that go into calculating the apparent magnitude, the absolute magnitude versus the apparent magnitude, and that sort of thing, that how can you really tell what the relation is?
Well, because that's where Sloan survey comes in, and that the genius behind it was that there's 2 million data points. So you can't fudge that.
Okay.
It's basically, if you go to a football, if you go to the Super Bowl, there's 60,000 people, and if you measure everybody, you're gonna find out that the average tall person is around 6 feet tall in America. In America, you go to a football game in America, you go to the Super Bowl, you're going to find out that the average, the top end of this of height is around 6 feet, 6 foot, 6'2", and then there's a few outliers, the people that are 6'6" or 6'8", the NFL, NBA players. Then you're going to find out that the short people around, adults are about 5 feet tall. And you're just going to get this. You're going to see that. You're going to and you're going to get 60,000 data points, and no one's going to be able to convince you that the average person is 2.5 feet tall or 8 feet tall, because you've got too much data.
So what your claim is, or your assertion is, that the redshift distance relation is not linear. Is that what you're saying?
Now, is it possible? I see this thing on the bottom. It says, want to share content? Ask your host to make you a presenter. Can I put something on? Can I show a picture? Is it possible?
Yes, I can do that for you. Just a second. Hang on. I'm going to.
Cool.
I got to find you in my list here.
I'm Alexander, because I changed to Alexander Mayer.
Here you are. Okay, here we go. I just promoted you. That gives you a few more bells and whistles that you wouldn't have had before. So go ahead.
Oh, wow. Share screen. Okay, hang on. Okay, go ahead. Let me just get this thing ready here.
We're all kind of new to this whole thing, so I'm sure there's a way to do it, but I don't know what. I can't tell you what it is. David DeHilster's here, and he probably can tell you, but I don't know.
I will have this for you in a second.
Myself. I know there's a way to share files. I just don't know.
Okay.
Let's see. Okay. At the bottom of the screen. You see the bottom of the screen, there's a little, it says share content or screen or add a note or whiteboard.
Yes.
That's where you go. So click on that, and then you get a little bar at the bottom, and you can click drag and drop files. You see that?
Correct. Okay, so I'm going to do share screen, and then I'm going to, you guys should see the Sloan Digital Sky Survey telescope right now.
Oh yeah, we see the telescope.
Did you upload the whole presentation?
I'm just going to give you the first few slides. I'm just going to show you. So this is it. This is the abstract. Don't worry about it. This is the stuff that's not. This is not the slides. This is coming up. Okay, but so here it is. Here's the data. Okay, so this is, you can see on the upper right, it says 961,000 galaxies. Every single point is a galaxy. The x-axis, right, is the redshift. The y-axis is the apparent half-light radius. This is the apparent, and remember, it's reversed. It's an inverted scale. So the big galaxies are at the bottom, and the little galaxies are at the top, just like a magnitude scale. So what we see, of course, is as redshift increases, the galaxies get small. They appear smaller. Is that clear to everybody? They're getting smaller because they're getting farther away. Just like if you look at something and you make it. A tree or something at 200 meters looks much smaller than the same tree at 100 meters. Okay. So
I have a
here,
real
by the
basic
way,
question. I've been playing with the screen to try to see what you're showing. It took me a while.
yeah.
I'm just wondering if what I'm doing controls what everybody sees, or if everybody individually has to move things around
Yes, we see
themselves.
it.
Okay, you see it. Okay.
I see it
So
now.
now
So I
look
don't
at
know.
this. So here it
I
is.
don't know if I'm the one that's because I
Me
had
too.
everybody's picture there. And I was trying to get rid of that, and I finally did. But now, is that what everybody saw, or is that just what I saw?
Okay, so here's the cool. We're getting to the really cool part. Now look at this.
All right,
This is the data, and it's beautiful. So here's the baseline, and you can probably see at the bottom. I'm saying, okay, well, we know what that is. Those are the largest galaxies. Those are. This is just the same thing as like looking at people that are 6'2", right? They 6'2". When you go walking, when you go to a stadium, the tall people, except for the outliers, are about 6'2". The kids are 4.5 feet. The short ladies are about 5 feet tall. So that's what you're seeing here, and of course, but you're seeing it in redshift. So of course, those big galaxies are getting smaller with redshift as they get farther and farther away. Okay, so the question is and then here is the average. So we're looking at this at the 5'6" people. The average, those black squares are the average size galaxies for those redshift bins. Okay, now here is based on the de cosine term. And you'll notice, by the way, the z plus 1 in the slides that are online from January, I made a little mistake. It's not a big deal. It was a very simple sort of interpretation. But this is the formula. This is correct. So here is the de Sitter prediction. Where remember the black lines that follow the equation say I'm the same size. I'm the same intrinsic size. So you can think of it, if you want to think of fruits. The bottom line is melons, the middle line is lemons, and the top line is peanuts, and it's just a peanut, and it's the peanuts getting farther away, so it looks smaller. This is the de Sitter prediction for sizes, and this is the lambda cold dark matter model. It's dead wrong. It's absolutely dead wrong.
Okay,
and
let me stop you here. This slide that we're looking at now, you're showing, I do see that it doesn't predict that well. What model is that?
Conventional
This is the
model.
lambda cold dark matter. This is the canonical consensus cosmological model.
Well, you're calling it LCDM concordance.
Concordance. It's called concordance, meaning everybody agrees that it's
I realize. Okay, so
model.
what does LCDM mean?
Lambda cold dark matter.
Oh, cold dark matter.
Yeah. Oh, yeah. This is it. This is the textbook. This is what all the big guns at the universities are hawking. Lambda. So this is the accelerating, expanding universe with dark matter.
Okay, it doesn't fit the data. We can see that. That's obvious.
Okay. Now what I'm going to now this is the same model with the. And by the way, this model is with the Hubble constant at the new and improved Hubble constant of 69.6. So it's called the 1% concordance. Again, everybody's agreeing. Everybody is, patting each other on the back.
So that's their fudge factor, and the fudge factor didn't improve it much. That's what you're saying.
So in other words, now if you switch to 100, like in other words, the Hubble constant does not change the shape of the curves. The Hubble constant, what you'll notice, only changes the distance, right? So you can look at the bottom at the predicted distances, like let's say 0.04. The Hubble constant here is so the distance is 164 megaparsecs, and here it's 114. That's what happens when you change. So the Hubble constant has absolutely no effect on the curves. Now, if we change, here is the pre-accelerating universe model. This is called the Einstein de Sitter cosmological model, where the lambda, right, where the cosmological constant is 0, right? And you'll notice that it's just that on these particular curves for what's called the theta z, it's just absolutely tiny. There's just really no difference. And then here, is the de Sitter, the empty universe, the empty expanding universe, where if you just set both but what you see is that these curves are dominated by the Hubble law, the expanding universe. So in other words, playing around with these constants, with these cosmological parameters, doesn't do anything for you. Now, let's just get now. This, by the way, we'll just keep going here. Okay, I just want to impress upon you that it's a done deal. So here is a plot of the volume of space as a function of redshift, right? So, for instance, in Euclidean space, the volume function is just 4/3 pi r cubed, right? In other words, if you double the distance, you get 8 times the volume, because and that's basically, it's really primitive. So you see that the dashed top curve is the volume of space is 4/3 pi times the co-moving distance cubed. And on the bottom part, where we're dealing with this, are you there?
Mm-hmm. Go on.
Yeah, so the bottom one, you see that it looks a little bit more complicated, but remember, there's no free parameters. It basically says the volume of space. Remember, there's that cosine term. There's the little cosine term. In this case, it's the arc cosine of 1/z + 1. That's how it comes in there into the volume, and it's spectacular. I mean, it's just as spectacular. I'm going to go quickly. I'm going to go back to this. Look at this. I mean, it's an amazing, and remember, these equations are a priori, meaning I didn't know anything about the data, nothing. The equations come from GR, from Einstein. I mean, it's properly interpreted. And here's the volume. There it is. And then,
well, it looks like LCDM is dead.
It's totally dead.
LCDM
and every variation of it is dead. So this is the volume, and these are the number of active galactic nuclei. And the cool thing about those is we know they're super bright. So you can see them. I mean, we were seeing them out to redshift 6 and 7, right? And you can just see the dots follow the line out. Remember that redshift 0.2 is pretty damn far away. I mean, that's a long distance. And so here you go. I mean, it's spectacular. And this data set is from NED. NED, you may recall, is the NASA extragalactic data system, which incorporates all the different surveys. So here's that data, and then here's when you do the differential dV/dz, which gives you basically, here you're doing the cumulative numbers of objects, and here you're doing the actual. This is the change in dV/dz. So here you're looking at the actual bin populations, and again, it's crazy. The standard model is so far off. The error is a factor of 10,000. And here's from Sloan Digital Sky Survey. Here's where the data comes from. By the way, all this stuff is, you can any one of you guys with enough time can just sort of duplicate this, because I give all the here's the Seyfert galaxies, right? And then here, I'm going to go through this just to show you. Here is the redshift magnitude data. This is the Sloan Digital. Here, look at this, 1.7 million galaxies, very accurately measured with the fiber optic cables, okay? So here's redshift magnitude. Remember that a smaller magnitude is a brighter object. So the bright galaxies are on the bottom. So the baseline is the bright galaxies, which are expected to be a standard candle, right, statistically. Here's the de Sitter. I'll call it the de Sitter model. It's not de Sitter, it's Alex Mayer's model, but it's based on this cosine term. You'll notice, of course, that as we increase in redshift, that the objects get a little bit brighter. They don't quite follow the line, but that's, of course, due to perspective, which is, I cover it right here. You see, because it's a fixed aperture measurement, so when you go far away, more of the galaxy is inside of the fiber, because it's a 2 arc second fiber. So you're going to get that little brightening factor. So anyway, here's the de Sitter, and here's the Big Bang. It's a joke. And remember that the supernova data that won the Nobel Prize follows the black lines. It's absolutely fabricated data. There's just no way. It's fabricated data. And
So Alex,
yeah.
This is really kind of interesting. Go on,
I'm
who's
come back to
talking?
my feed.
You got a question?
I just would like to have a little bit more, just because I see the graphs, and it's easy to see that like some graphs match and some graphs don't, but I'm still having a hard time grasping why that is. Like, can you get a little bit more color around what's actually happening? What is the data actually showing? Because it looks like there's some relationship between the redshift and the apparent brightness of the galaxies. Are you saying that the redshift, that there is a dependency like that? Because you wouldn't expect there to be dependency like that.
Okay, so what these graphs show beyond a shadow, first of all, they show that yes, can you hear me?
Speak up.
Hello?
Yep.
Okay, so what the graphs, remember that physics is about making an accurate prediction. So the math predicts, it says, okay, what is the relationship between redshift and size? What is the relationship between redshift and the volume of space? And then the third thing is, what is the relationship between redshift and the apparent brightness of an object of the same brightness, like a 100-watt bulb, okay? And so what you see there is that there is the I'll call it the de Sitter model, okay? The de Sitter model follows the data. It's accurate, okay? And the expanding universe model, which assumes a linear, the Hubble law model, is not just wrong. It's just radically wrong. It's completely wrong. And the beauty of Sloan Digital Sky Survey is that the data, there's so much data, and it was automated that they couldn't massage it. They couldn't, they just gathered the data and put it on the computer.
Let me clarify this point. What are they using a model to correct the absolute magnitudes? You're saying they're not.
They're not. There actually turns out to be a little bit of an error in what's called, there's some kind of systematic error, which I point out in the Trojan radius data, but it's not in the half-light radius data. And then the fiber now, did you know that those fiber magnitudes that I showed you that are just so amazing, they were like nobody's considering
Alex,
those
you're
to be
getting
scientific
a little bit
data.
into the esoteric fine points.
Okay, so in other words, I'm the first guy to plot that data.
Okay, wait a minute. Okay.
Most people don't know how to extract it. No, I'm just saying.
Is your
those are graphs that don't exist.
Is your data showing a relationship between redshift and the magnitude? That's what it looks like. That was my main question. Is there a relationship between the redshift and the magnitude?
Yes, there is a relationship between the redshift and the magnitude, and it's predicted.
You're telling me like the brighter galaxy has a greater than expected redshift, and I just want to get this point straight, because the normal cosmological model, the regular cosmological model, is that there shouldn't be any relationship between the brightness or the magnitude of what you're looking at versus the redshift. I always presume that if something was a certain distance out, that all the objects at that distance would show the same redshift. But you're saying that the data absolutely doesn't say that.
No, of course not. Of course, if they're at the same distance, then if they're at the same distance, then the redshift is the same. But the magnitude is how bright an object is. So if you take a 100-watt bulb and a 10-watt bulb and a 1-watt bulb, and you put them all out at the same distance, well, it's just they'll be less bright than if they are close by, but there'll be an order of magnitude difference in the brightness between those three objects. right? Because one's 1 watt and one's 10 and one's 100. So the assumption, which is,
but I would expect that
very
if
well,
those bulbs were all retreating away from me, that the redshift would be the same.
they're not retreating away. It's irrelevant about we're not talking about whether they're retreating or not. We're talking about the relationship between how bright they are. I mean, in a Euclidean space, okay, you can use a camera. You can get your Nikon.
Well, I think we are absolutely talking about, we're talking about redshift. So we are absolutely talking about the situation.
But we're interpreting redshift as we're interpreting.
Alex, could I interrupt here a little bit?
Yes, sure.
I think the real question that needs to be asked is, there are no, in the Sloan data, they're not using cosmological models to correct the apparent magnitudes to absolute magnitudes?
Correct. Those are apparent magnitudes. Exactly.
So what we're talking about is we're talking about the uncorrected measured data.
Correct. And everywhere you look in the literature, it's ridiculous. They don't show you the original measurements. So-called corrected measure, exactly, which is ridiculous. It's not the data.
Correct.
You never see.
Your assertion is you're dealing with the actual data. So
correct.
What you're doing is you're plotting apparent magnitude versus redshift. Is that not correct?
Correct.
Okay.
Correct.
Apparent magnitude, which is how bright it is measured on the Earth, and that
it's literally measured by the CCD.
Correct.
Really accurately.
Okay, so, and then you're plotting your you're taking your cosmological prediction and putting it on there as your curve. Those are the curves that you're putting on there.
Correct.
And your curves fit the data better than the mainstream curves.
I think better is,
That's the conclusion I get. Okay, I think I understand it. Frankly,
so there's no distance. So the graphs there actually don't include any distance consideration, right?
Correct.
That's just
What
brightness
do you mean by
against
distance?
redshift.
Alex, can you download this data from somewhere?
Yes, everything. By the way, if you go through my slides, it'll take you a while. The slides that are online right now, which, as I said, there's a small correction factor, and I'm going to update them.
No, but I would like to download the raw data from NASA.
Everything you need to know is in my slides. If you download my slides, it gives you everything you need to reproduce everything from scratch.
Okay.
There's no secrets.
I have some comments on Sloan Digital Sky Survey.
Go ahead.
Okay.
Herman. It's Herman.
Herman, go ahead. Speak up.
There is work done to test Sloan data for Alcock-Paczynski test, right? And this test is about how uniformly the volume is filled with galaxies. And I will put the reference to the paper into the chat, which everybody can see. And this work was done by Martin Lopez Corredera. So he tested several models against this test using Sloan Digital Sky Survey data. And what he found that there are two models which satisfy Alcock-Paczynski test is concordance lambda CMD and static universe with direct light redshift. He said they are equally well satisfied. I will upload it. It's not my research. It's research of the scientists. So I will upload, I will put the reference to the chart, and you can read it and argue with him or compare the results of Alex and Martin Lopez, right? Okay, here it is.
Okay, just as a comment, Alex.
Everybody can see this? Everybody can see this in the chart?
Yeah, it's great.
Okay, thank you.
Alex, I want to make sure you get together with Greg Volk and get a Saturday morning so you can present this in more detail and get more questions.
I shot you an email earlier, Alex, and all you need to do is reply and just send me an abstract and a Saturday that works. We meet at a lot of Saturdays.
Herman, I'd say
You know,
the same thing. And, if you have anything to contribute, talk to Greg Volk.
Okay, for the either cosmology, right?
Um,
We were talking about some session about either cosmology. That's what I'm kind of practicing.
Greg Volk,
Yeah.
talk about whatever topic you want.
yeah, we're pretty open as far as that goes. As long as you don't talk about baseball, you can talk about the physics. You don't talk about baseball.
It has to be.
Or
I'm
politics.
noticing that somebody named Sujak wants to say something.
Yeah, it's, I've been ignoring. People have been raising flags, and Harry's kind of running the show here today, so I've been ignoring that. But I think it works pretty well for people to just kind of step right in and just assert yourself rather than wait.
Hans,
I don't know how to deal with the flags. Actually, it's not the same as it used to be. So, and it's also I kind of hate to step on Harry's shoes. So
I can't really see what's going on, Greg. I mean,
there are flags.
There's so much. There's so many pictures on my screen.
I know it's good. I don't know how to respond to it the way we used to, but there are flags.
Okay, well, who's Sujak?
Yeah, why don't you go ahead and
yeah. Hello, Sujak.
He's mute. I think.
Oh, there he is. Okay, great.
Speak up.
Hi, Sujak.
Can't hear.
Go ahead, speak
He's
up.
not muted, but he's not saying anything.
He's speaking, but we can't hear.
You got to unmute your microphone. It's down at the bottom left. There's a microphone icon, and if it's got a red bar on it, you have to click on it and unmute it.
No, he should be unmuted now.
Okay, go ahead.
He is unmuted. I think there's a difficulty with Sujak. Your sound is just not working. Something on your end. Sorry, you're going to have to deal with it because you are unmuted. I don't know what's going on. So we'll have to move on. Sorry.
While perhaps you're dealing with that or somebody else, could I just ask a quick question? Ian Cowan here. Basically, with the traditional GR metric, you have this redshift, and you have the cosmological constant and all that sort of thing, lambda, and you have the redshift. Now, you seem to have, Alex, a modified metric with this cosine squared term in it, which appears from the graphs to fit better the data. Now, but my question to you is, what do you say is causing this redshift? Is it a curved space time?
Yes, it's time dilation. It's pure, and it goes all the way back to Minkowski, and it's really interesting. So Minkowski, in about 1907, Minkowski gets this paper written by his former student, who he thought was an idiot. I mean, he literally thought Einstein was like very bad in math and lazy, and the guy never went to class because he was screwing around with girls and everything like that in the coffee houses. So he gets this paper, and Minkowski's a super genius, brilliant mathematician, one of the best. Okay, so he reads this paper and he just says, "Oh my God, I can't believe it," because he knew, of course, that it was a work of genius, right? But he says, "I can't believe that this idiot student of mine did this," but he said, and this is the great part. He goes, "Well, but of course he got the math all wrong, because he was using algebra." So, the metric, the Minkowski metric. So Minkowski, when we talk about space, first of all, space-time, that's not Albert Einstein. That is Hermann Minkowski, okay? That's right. The math genius. So space-time.
So that's the Minkowski
metric.
That's the Minkowski space. Sorry to interrupt you,
correct.
But just to clear it, that's the Minkowski space on which this metric is based. But I mean, this correct. Is basically a special relativistic basis. So my assumption is that you personally accept special relativity as basically quite correct. Is that so?
It is quite correct, except the interpretation. You see, the algebra of the Lorentz transforms Now, so here the tragedy is that Minkowski died of appendicitis in January 1909. I am confident that if the guy had lived another year, let alone because he was 42, he was a young kid. I mean, not kid, but he's a young guy, right? If he would have lived another few years, he would have, this whole thing would have gone away because he really understood what was going on. And what he did is he geometrized time. Now, here's the interesting thing. So it is documented that Einstein said that the work of Minkowski, when he was first exposed in 1909, right after Minkowski died, and somebody showed him these lecture notes, right, and the mathematicians, remember, Einstein was not a mathematician. He was a crap mathematician. He was just this awesome thinker, right? Okay, so he gets this paper, and he's really young. He's what, 20? He was 27 at the time, and he was arrogant. Einstein wasn't arrogant. He wasn't perfect. So he said, oh, this stuff is superfluous. He used it in German, superfluous erudition. He was like, oh, this Minkowski, I remember him. He was my professor. And he's just trying to rain on my parade. He's just, this is not even worth anything. Okay. Now, a couple years later, he's working on GR, general relativity, and he's struggling and struggling and struggling. And of course, he has to go back to the concept of metric. Remember, because a metric is an equation that measures the distance between 2 points in a space. So Minkowski metric is basically, it's called pseudo-Euclidean because you've got this negative sign in the time term, which has to do basically that's special relativity. That's all. It's in a nutshell. Okay, but it's measuring this distance between points. And of course, like let's say here's my space, right? This is a piece of paper, and it's Euclidean. But as soon as I can measure the distance between these 2 points with a what? A squared minus, if I say 0.
Alex, I think we all know all this. I mean,
Okay, well, if you curve this space.
So Harry, and also Alex, if I may just talk over you a little there, just for a second, because I think what Harry was trying to say. I just one more thing I might say, if you permit me. I think in your presentation, which we'd be looking forward to, you would need to convince people that your system is more than a fortuitous curve fit to the Sloan data study.
It's not a curve fit.
It's based.
No, that's really bad.
It's based on a time dilation which many, for my part, I'm one of them, believe that there's very strong empirical and theoretical evidence taking the whole bottom out of that and establishing that actually it isn't the case. So the physical basis of what you're saying is perhaps something that you will need to address when you give your talk. Thank you.
Okay, but there's no curve fit. There's no curve fitting. There's no free parameters. If you look at the equations, there's no free parameter to allow for a curve fit. There's no curve fitting. You get what you see is what you get.
Your curve does fit the data for whatever reason, but
but
you haven't given a physical.
It fits the data because it's correct. It's correct.
You say it's correct because it's based on a modified special relativity theory.
There's nothing simpler than V equals IR. Okay, the voltage is equal to the current times the resistance. Okay,
all right.
And if you
we're getting towards the end here.
I want to make one more comment. Alex, your metric has to fit other criteria. For example, conservation of momentum, all the relativity tests like bending of light, and all this you have to prove. You have to write down your metric, and you have to prove that it's satisfactory.
I've done that. Okay, gentlemen, I've been working on
delay, and all that which has been measured.
Physicist. And you're telling me, okay, there's a lack of communication here. You're talking about curve fitting. You're asking me stupid questions like you have to make this work. Do you think I don't know that? I'm a professional.
But show it.
I don't know that. I'm showing you something that you're the ones that need to do. I'm sorry. You're the ones that need to do the homework. Okay, it's out there. It's already done, and the people in charge know it, and they're trying to cover it up. So please don't tell me that I need to do my homework because I've done my homework. I've done my homework. And it's
Alex, I think we'll look forward to continuing this discussion at a later date.
Okay.
We're moving on here till 11:57.
All right. So
It's
very.
I appreciate you coming by and telling us about this. That's certainly something I didn't know about, and I think that what I think my idea was to have a discussion so that we would get people like yourself to come and talk about this, so we would be exposed to new things. Okay, that's what the purpose of this open discussion is all about. And you've really done that. I think this is just wonderful. Whether you're right or wrong or convinced, that's a matter of convincing people here. That's another issue.
Yeah.
Thank you for coming by and talking to us.
Thanks for this opportunity. I think it was, and
everybody else, I thank everybody else for coming by as well. I'm totally stunned because I learned a lot. I learned things I didn't know. Thank you. So I guess unless we have somebody else who wants to talk, it's 12 o'clock, so it's time to get off of here. Greg?
Okay. I guess I have my mic on. Let's see. What do I do here?
Can I make an announcement here, folks?
Sure, David.
We do have a conference coming up. It's about 4 months and something. I have 8 people said they're going. We have about 4 abstracts. I'm going to be putting up a time limit to when I'll have to cut off to say this is going to happen or not happen. So one of the things we don't want to do is procrastinate and wait to the last minute because of what's happened in our organization. We don't have a bank account to go out there and make deposits on things. So we really need you to go to the website, at least say you're going. I'll be having the registration information there. We need to have abstracts and we need to have bodies at the conference itself. Now I have a limit to where I think it's about 40, worst case 40 people at the conference physically paying their dues, which is going to be $125 this year. And then we have also, I calculated only about 400 pages in the book. So I've got it calculated low, but right now we don't exist. Everybody wants it, everybody likes it, but we need action. So it's simple. If the membership wants this, then we need all of you guys to start acting upon that, especially the abstracts, and just at least saying, sign up on the website, say, I'm going. So we get an idea that I'm going to have a go, no go coming up here soon. Okay, that's my announcement.
Okay, good. Thank you. And so I would encourage those of you who have been putting your papers in VIXRA or other various places, consider publishing them in our proceedings. We're not exclusive. You can publish them elsewhere also, but it's another avenue for you to do that. And so now's the time. All right, and look forward to having more discussion on this idea. I'm looking at your website. Now, Alex, before we close, is there one particular paper that kind of generates these curves? You said everything would, if we looked at and I did look at your presentation, and I guess I was hoping for a reference to a paper or something where I could see how you got these curves.
Okay, so all of the curves are developed. The slides, if you go to the last slide of the because I purposely the one you download is whatever, it's a small number of slides. The last slide references the full slide deck, which is 400 slides. Okay, and it's basically because it's highly graphical content. There is no paper yet. Now a paper should go out to the archive shortly. But,
okay. Yeah, I'm not interested in graphs. I'm interested in formulas, to be honest, and then I can generate my own graphs.
Well, the formulas are all there and they're all derived. Okay, and and I really don't appreciate that tone. Okay, because you don't. Okay, everything is there. Everything is there. Everything is derived from first principles. So don't do that tone with me, because it's condescending, and frankly, it's unacceptable. And everything you need is there. All the formulas are there. All the facts are there. All the data is there. Everything can be duplicated. I'm a professional. And I'm not here to waste anybody's time. So go ahead and do your homework. It'll take you a couple of weeks, I imagine. because there's a lot of material there, and you're probably going to have to, do a little bit of, work in mathematics. You're going to have to start, you probably want to know, what rotations are at 4 dimensions and things like that. Probably good idea. But everything you need is there. I'm not here to waste anybody's time. I'm not a theorist in the sense that I'm putting out some theory that might or might not be correct. It is correct. And right now it's a matter of time, and I'm just hoping it's less than 20 years before they start teaching this in high school.
All right. Well, thank you.
All right.
Can we sign off, Greg?
Sure.
Recording.
Close out the recording.